Hello everyone and welcome you all in the problem solving class of the course Applied Electromagnetics for Engineers. I am Vivek Kumar Srivastava, TA of this course. So the today's class is completely devoted to the topic vector algebra and Maxwell's equation. So we will see some of the numerical based on these two topics. Okay, so let's start. So here is the first problem. So the question states that which one is incorrect. Okay, so the statement is gradient is a scalar operator that gives direction of maximum rate of change of a quantity. Statement B says that divergence is a vector operator that measures the magnitude of a source or sink at a given point. Statement C states that curl is a scalar operator that describes the rotation of a vector field, whereas statement C says that both A and C is incorrect. Okay, so we have to find out that which statement is incorrect. So as we all know that gradient is basically a scalar operator. Basically gradient is applied on a scalar function. Okay, so basically this quantity basically represents the direction of the maximum rate of change of a quantity. Okay, that in which direction the rate of change of a function f is maximum. Okay, whereas the divergence is a vector operator. So this statement is also true that divergence is only applied on a vector field, and basically this quantity represents the magnitude of source or sink at a given point. So basically if suppose this is a point at which we are determining the divergence, so basically this represents whether this point contains any source or not. Like if suppose it have any source, then the divergence will be positive. Okay, so in all the direction, like divergence will be positive. So this represents that flux is emanating from this point. So basically this statement is correct that if the divergence of any function vector function at any point is positive, then this represents the positive divergence. Okay, whereas if suppose this point is not contains any source, then the field which will emanate inside this point. Okay, so this will act as a sink here. Okay, so this statement is also correct. So statement C states that curl is a scalar operator. So basically curl is not a scalar operator. Curl curl is also a vector operator. So basically this is basically applied only on the vector fields. It is not applied on a scalar field. Okay, so this statement is incorrect, although the rest of the statement is correct, only that it describes the rotation of a vector field. Like if suppose you are calculating the curve of any vector field, so it represents that in which direction it is rotating. Okay, whether it's clockwise or anti-clockwise. So this represents the curve. So basically here option C is incorrect. Okay, so let us, so here option C is incorrect. So let us move to the next question. So the next question states that if R is given as x plus y plus z means R is a vector quantity, and t is given as it is also a vector quantity but function is different, obviously, then we have to determine del dot r into t. Okay, so here this r and t basically a vector quantity. Okay, so for determining r del dot r into t, what we will do, we will first calculate this del dot r. So basically del dot r we can find out as uh, del by del x into ax plus del by del y into ay plus del by del z into az. Okay, this will be and here r is x ax plus y ay and ZAZ. So you can calculate this. This is not only del by del x of x plus del by del y of y plus del by del z of z. So this will be equals to 3. Okay. So basically the value of del dot r is equals to 3. So you have to multiply this 3 with this vector quantity t here only. Okay. So del dot r to t is equals to 3 into 2zy ax plus x y square ay plus x square yz into az. Okay, so you can multiply this 3 inside this. So the correct option is, yeah, so you can multiply this quantity inside. Okay, so the correct answer you can calculate like option number 8. Okay, so let us move to the next question. So here it states that r is given as xax plus yay plus zaz, which is a positional vector of the point x comma y comma z, and p is defined as modulus of r, means magnitude of r, and n is an integer. So we have to basically find out this del cross r, p to the power n into r. So we have to find this quantity. Okay, so for finding this out we have to first calculate the value of p. So here value of p is given as modulus of r, and r is a positional vector here. So r as defined here, so magnitude of r is given as x square plus y square plus z square raised to the power 1 by 2. Okay, so this is basically the value of p only. Okay, so p is defined as this quantity. So we have to first find out the value of del cross p raised to the power n. Okay, so you can put the value of p here. So we have to find the value of del cross x square plus y square plus z square raised to the power n by 2. Okay, so yeah, and also you have to multiply this with a vector of r. Okay, so r is already given here, which is equals to x ax plus y ay plus z into az. Okay, so you have to multiply this, and then you have to calculate the curl of this vector, so which is given here. Okay, so this curl can be calculated as ax, ay, az, del by del x, del by del y, del by del z, and this quantity you can multiply inside this vector quantity. So the first quantity which is written here is basically a multiplication of x with this quantity. Similarly, the second quantity which is written here is the multiplication of y with this quantity. Similarly, the zx component is a multiplication of z into this quantity. Okay, so you can calculate the curl, and once you calculate it will come to 0. So option D is correct here. Okay, so let us move to the next question. So here in the question it is given that the flux through each turn of a 50 turn coil is given as t cube minus 2t milliweber, where t is in second. So we have to find out the induced EMF at t is equals to 3 seconds, that how much voltage will be induced in this 50 ton coil. Okay, so this can be calculated by the basics of Faraday's law of electromagnetic induction, which states that the voltage induced is given as minus n d phi by dt, where n represents the number of turn and phi represents the flux. Okay, so you can put the value of n and phi here, which is equals to minus 50. Yeah, here you can put the value of phi, d by dt of t cube minus 2t. Okay, this will be milli. So you can calculate this d by dt term, minus 50 into 3t square minus 2 milli. And after that you can put the value of t as 3 seconds, which is given in the question. So you can calculate this. So the induced voltage will be determined by this term. Okay, so you can calculate it, and the answer that you will found is minus 1.25 volt. So option C is correct here. Okay, so let us move to the next question. Find an approximate value of total charge enclosed in an incremental volume of this, which is given as 10 raised to the power minus 9 meter cube, located at origin. Okay, so let us suppose this is my coordinates in uh, coordinate axis. Okay, and we have to consider a small incremental volume here, which is located at the origin. Okay, so this small volume is located at the origin, and we the flux density that is emanating from this small cubical surface is given as this. So we have to find out that what will be the total charge enclosed in this incremental volume. Okay, so for finding out this charge enclosed, what we have to do, uh, we have to first know that what Gauss statement says. Okay, so Gauss's statement says that if suppose this is a volume, inside this some charge q will be present. Okay, so the flux emanated by this charge through this surface is defined as, yeah, surface integral of d dot ds is equals to, yeah, this will be rho only, this will be equals to rho. So this will be valid throughout this Gaussian surface. Okay, so this will be the amount of total charge that is enclosed inside this volume. Okay, so this statement can also be written in the point format. So for that you have to first write this q as uh, volume integral of rho v dot dv, where rho v represents the volume charge density, and for representing this statement in the point form you have to take the uh, help of Gauss divergence theorem. Okay, where you can represent this surface integral by volume integral as volume integral of del dot d into dv is equals to rho v, volume integral of rho v dv. So from here you can come up that del dot d will be equals to rho v. Okay, so we will use basically this uh, formula for solving this question. So here also you can see that d is given as this quantity. So you have to first find out the value of del dot d. So this basically represents the total charge enclosed in the incremental volume, which is located at the origin. Okay, so you can calculate this as del by del x into ax plus del by del y into ay plus del by del z into az dot e raised to the power minus x sine of y into ax minus e raised to the power minus x cos of y into ay plus 2z az. Okay, so you have to individually basically take derivative that is e raised to the power minus x sine of y, then minus del by del y into e raised to the power minus x cos of y, then del by del z of 2z. Okay, so you can calculate this differential term, and the differential term is given here. So once you calculate, you will see that this term will be cancel out each other. Okay, so the remaining term will be equals to 2. Okay, so uh, yeah, so the total flux that enclosed in the incremental volume which is given here is basically represents the multiplication of this term into this incremental volume. So the total charge enclosed will be 2 in nanocoulomb. Okay, so let us move to the next question. So this question states that the cylindrical surface rho is equals to the cylindrical surface rho is equals to 8 centimeter contains the surface charge density rho s. Okay, so we have to find out that what is will be the total amount of charge present, okay, on the cylindrical surface. So if suppose this is a cylinder having infinite length, because length is not mentioning here that how what will be the height of this cylinder, or say z. Okay, this will be z, and yeah, rho will be given here, which is equals to 8 centimeter. Okay, so the total charge that is present on the surface, means on this surface, is given as rho s is equals to 5 e raised to the power minus 20 modulus of z nano coulomb per meter square. So we have to find out that what will be the total amount of charge present on this cylindrical surface. Okay, so for finding out this, we have to first take a, yeah, Gaussian surface here. So this is basically my Gaussian surface. Let me change the color. Okay, so this is my Gaussian surface, such that the such that this cylindrical surface will contain inside this Gaussian surface. Okay, so the total amount of charge present, yeah, in total amount of charge present that we have to calculate is defined as surface integral of rho s into ds. Okay, so this is my coordinate system, and this represents the x, this represents the y, and this represents the z. So z basically start from 0 to infinite, and phi goes from 0 to 2 pi. Okay, rho s is given as 5 e raised to the power minus 20, okay, into z into rho d phi into dz. So the value of rho is given here as 8 centimeter, so I can replace this as 0.8, 0.08, sorry, this will be equals to 0.08. So basically we have to calculate this uh, integral so as to find out the value of total charge that will contains on this cylindrical surface. Okay, so you can find out this. So once you find out the integral, the total amount of charge that is present on the cylindrical surface will be given as 0.25 nanocoulomb. Okay, so after that, the second statement states that how much electric flux leave the surface rho is equals to 8 centimeter, and z from minus 1 centimeter to 5 centimeter, and 5 from 30 till 90 degree. Okay, so to find out the value of flux, what will we will do? So from Gauss statement, it states that the passing through any surface flux that is passing through any surface is equal to charge enclosed inside that surface. Okay, so basically we have to find out the that how much will be the total charge inside the surface that is given here. Okay, so that we have to calculate. So basically here the for finding out the total charge that is enclosed inside the surface mentioned here in this question, what we will do, we have to integrate the jet from 1 centimeter to 5 centimeter, and 5 from 30 to 90 degree as mentioned in the question. And here the rest part will remains the same as is in the a part of this question. Okay, so after calculating this, you will find out that the total charge that will contains inside the surface that is mentioned in the question is given as 9.45 picocoulomb. So we can say that this much amount of flux that will leave through the surface. Okay, so that's how you can calculate that how much flux is emanating from any surface. So let us move to the next question. So the next question says that evaluate the total charge enclosed in the parallel peptide formed by the plane x is equals to 0 and 1, y is equals to 0 and 2, and z is equals to 0 and 3. Consider the electric flux density inside the parallel peptide is given as this term here. Okay, so first of all we have to see uh, that how this parallel peptide is representing in uh, coordinate axis. Okay, so x varies from 0 to 1. So if suppose this is my x, this is my y, this is my z. Okay, so x start from 0 till 1, y start from 0 till 2, and z from 0 to 3. Okay, so this is how my parallelepiped will show in coordinate system. Okay, so this will be from 0 to 1, 0 to 2, and 0 to 3. Okay, so from here we can see that the electric flux density inside this parallelepiped is given as 2xyax plus x square into ay. So from this expression we can say that flux emanates only from x-axis and y-axis, whether it is from front side and back side, left side and from right side, and no flux will emanate from the top and the bottom. So only flux will emanate from x axis through the surface area which is along the x-axis and y-axis. Okay, so the flux component uh, or say dz will be equals to 0 here. Okay, so so for finding out that what will be the electric flux density inside the for finding out the total charge enclosed in the parallel peptide, what we will do, we will use Gauss theorem, which states that, as I said earlier, that the total amount of flux emanated from this surface will be equals to the charge enclosed inside this surface. Okay, so this is represented as q is equals to surface integral of d dot ds. Okay, so we have to take here uh, if suppose we are standing on x is equals to 0 and x is equals to 1. Okay, means it represents that the back, yeah, front and back surface. Okay, so we have to take z constant here, sorry, x constant here, which is equals to 1, and for this surface we have to take z is equals to 0, sorry, x is equals to 0. Okay, so the flux that is emanating through this surfaces, okay, is given as d at x is equals to 0. So this represents the bottom one, sorry, this represents the bottom surface, not bottom, it's a back surface basically, back surface, flux emanating from the back surface, and this second quantity represents the flux that will emanate from the front surface. Okay, so that's why x will be fixed here, and the remaining quantity, that is y and z, will be variable here. So you can see that y will be variable here from 0 to 2, and z is also a variable from 0 to 3. Okay, so that's how you can calculate the flux that is emanated from the front and the back surface. Similarly, for calculating the flux emanated from the right and the left surface, you have to take uh, y constant here. So basically, let me change the color here. So basically this represents the left surface and this represents the right surface. Okay, so now we have to calculate the total amount of flux that is emanating through these surfaces. So we have to take y as constant here, and the rest quantities, that is dx and dz, will be variable here. Okay, now one thing that you have to take consider here, the amount of the direction of surface area, because as we know that surface area is a vector quantity, so you have to define the direction as well. So like for the front one, you have to say that here the surface area, differential surface area, is defined as dy dz into ax, whereas for the back surface you have to define the surface area ds as dy dz into minus ax. Okay, this will be minus ax. Okay, because the direction of this surface is opposite to the positive x-axis. Similarly, here for the right hand surface, you can define the surface as, yeah, dx dz into ay, and for this surface you can define it as ds as dx dz into minus ay. Okay, so that's how you can take the surface area. So that's what I am taking here. Okay, now you have to just calculate this integral so as to find the total amount of charge that is enclosed inside this parallelepiped. Okay, so once you calculate, you will find out that the total amount of charge that is enclosed inside the parallelepiped will be 12 coulomb. Okay, so basically this will be very hectic for one to calculate this integral. Okay, because here in the question the uh, electric flux density is a simple basically function here. Okay, but for the complex function we cannot calculate this integral. So for that we can use one of the simplest thing, that is the Gauss divergence theorem, which states that surface integral of d dot ds is equals to volume integral of del dot d to dv. Okay, so we can calculate this divergence of d very easily, because d is given here as 2x y ay plus x square ay. So similar, so you can find the divergence of d as del by del x ax plus del by del y ay, oh sorry, dot, yeah, what is mentioned here in the question, 2xy ax 2xy ax plus y square ay. sorry, plus x square ay. Yeah, so here it will be x square ay. So you can calculate this very easily. So this will be equals to 2y plus this will be 0 because there will be no y term present in the yx component. So this will be equals to 2y. Okay, so you can calculate the divergence of d first, and then for calculating the volume integral you have to just integrate this volume uh, from 0 to 1 along x-axis, 0 to 2 along y-axis, 0 to 3 along z-axis. Okay, then also you will get the same result, which is equals to 12 coulomb. Okay, so that's how you can calculate the amount of charge present inside any surface. So you can take surface integral like here, and you can also adopt this uh, diver yeah, Gauss divergence theorem for calculating this. So from here you can see that it will be very easy. Okay, so that's why we can also use Gauss divergence theorem. Okay, so let us move to the next question. So this question states that a spherical surface at r is equals to 2, 4 and 6 meter carry a uniform surface charge density of this and this respectively. So we have to find the d at 1 centimeter, 1 meter, 3 meter and 5 meter. This is the first part of this question, and the second part states that determine the value of rho s naught such that d will be 0 at r is equal to 7 meter. So first of all, let us first understand this question by pictorial way. So if suppose this is radius r is equal to 2 meter. Okay, so this contains the charge of 20 nano coulomb per meter square. So this will be surface charge basically. Okay, similarly, oh, 1 minute. Yeah, so the second surface will be at r is equal to 4 meter. Okay, and the charge contains by this surface will be equals to rho s is equals to minus 4 nano coulomb per meter square, and the third surface is at r is equals to 6 meter, and this will contains the surface charge of rho s naught coulomb per nano coulomb per meter square, whatever you can say. So we have to find out that what will be the value of d at r is equals to 1, 3 and 5. Okay, so r is equals to 1 will, oh, 1 minute. Yeah, so r is equals to 1 will be inside this r is equals to 2 meter radius, and as you know that there will be no flux, there will be no charge inside this radius r is equals to 2 meter surface. So the charge inside uh, this r is equals to 1 meter radius will be 0. Okay, so from here you can say that from Gauss law is equals to q, so this will be equals to 0, or say d will be 0 here. Okay, so the inside this r is equals to 1 meter radius will be 0 here. So the next will be 3 meter, so 3 meter will be in this range. Okay, so this will be my radius, r is equals to 3 meter. So the total charge that enclosed inside this r is equals to 3 meter will be the charge present at this r is equals to 2 meter spherical surface. Okay, so first of all we have to find that how much charge will be present. Okay, so for that, what we have to do, okay, so here this is not charge, I'm sorry, this will be, yeah, this will be density, not charge. Okay, yeah, this will be density here. Okay, that is given, volume surface charge, uniform surface charge density. So for calculating that how much charge present on this surface, so what we have to do, as we know that charge present is defined as d dot ds. Okay, so this will be equals to 20 nano coulomb per meter square into 4 pi into radius will be 2 square. Okay, so this much charge will be present on this surface. So the flux, or say d, that is emanated through this r is equals to 3 meter surface, is given as d into 4 pi r square is equals to charge enclosed inside this. So this will be equals to 20 nano into 4 pi into 2 square. Okay, so 4 pi will be cancel out here, and r you can put here as 3 square. So that's how you can calculate that how much flux will be emanate through this r is equals to 3 meter radius. Similarly, for finding out, yeah, so for finding out that how much flux that will be emanate through r is equals to 5 meter radius. So the total charge that is enclosed by this r is equals to 5 meter spherical surface is defined as q is equals to d, which is equals to 20 nano coulomb per meter square into 4 pi, r will be 2 here, 2 square, plus one more charge will be present at r is equals to 4 meter radius, and this will be defined as minus 4 nano coulomb per meter square into 4 pi into 4 square. Okay, so that's how you can calculate that how much charge will be present inside this r is equals to 5 meter spherical surface. Okay, so once you calculate this, you can equate this, and is equals to d into 4 pi into 5 square. So this 4 pi will be cancelled from each side, and you can calculate the value of d. So that's how you can calculate the value of d at any spherical radius, for any spherical radius. Okay, now the second part states that we have to find the value of rho s, which is present at r is equals to 6 meter radius. Okay, such that for r is equals to 7, here r is equals to 7 meter radius, the flux density will be 0. Okay, so for calculating this, what you have to do, yeah, so basically you have to use the same uh, procedure that we have followed. So basically, for calculating this, what you have to do, you have to equate yeah, sorry, this will be 20. First you have to calculate the total charge, which will be equals to 20 nano into 4 pi into 2 square, plus minus 4 nano into 4 pi into 4 square, plus rho s naught into 4 pi into 6 square. Okay, so this will be the total charge that is enclosed inside this r is equals to 7 meter radius of a spherical surface. Okay, so you have to equate this from d into 4 pi into 7 square. Okay, so 4 pi you can cancel from each side, So that's how you can calculate the, okay, d will be 0 here. Okay, so you can directly put the value of d as 0 and you can calculate the value of rho. Okay, so that's how you can calculate the value of rho here. So let us move to the next question. So here it is given that consider the region defined as modulus of x is, comma modulus of y comma modulus of z is less than mod of is less than 1. Okay, means in the coordinate system it is defined as x, y and z. So x will be start from minus 1 to 1, y will be start from minus 1 to 1 and z will be start from minus 1 to 1. So okay, and epsilon r mu r it is given as 5 and 4, sigma will be 0 here, jd that is, yeah, jd displacement current density is given as this. So we have to find out the value of d and e. So as we know from Maxwell's equation that jd is defined as del d by del t. Okay, so from here we can say that d is equals to integral of j dot dt plus c. Okay, so here jd is given as a function of time, so you can integrate this jd say with respect to time and then you can calculate the value of d. Okay, so that's how you can calculate. Okay, and for determine the value of e, what you have to do, as we all know that e as defined as d by epsilon and d is given as you have already determined, and epsilon is defined as epsilon naught into epsilon r. The value of epsilon r is already given in the question, which is equals to 5, and epsilon naught value of epsilon naught we already know that it is equals to 8.85 into 10 raised to the power minus 12. Okay, so you have to just put the value and calculate the value of e. So this will be the answer once you calculate. Okay, so I hope that this session will be informative to you. So this is the last problem of this class. So thank you everyone.